Welcome back to the Professor's Du Bois channel. In this video, we are going to continue our A Closer Look series with gas laws.
All right, so let's start out by reviewing Boyle's law. And Boyle's law was looking at the relationship between pressure and volume. And if we graph this relationship, you can see this graph here, we can see that at very high pressure, we have low volume. And at low pressure, we have a large volume. So we can call this an inverse relationship. And looking at this graph, we can say, you know, there's definitely a trend here. We can see it's not a straight line, though. It's a curved line. Now, if we plot, instead of volume, if we plotted 1 over volume on that x-axis against pressure, we then get a straight line that has a positive slope. Now we actually have a relationship. So we can say that pressure is proportional to 1 over volume. And we use this funny little symbol. It's not really an equal symbol. It just means it's proportional. But you know what? We can make it equal if we multiply by like a constant of some sort. So we'd have to figure this out. We'd have to have a constant temperature and a constant amount of gas, but we could figure out what the constant is such that 1 over volume, we multiply it by it and get the pressure. So moving forward, we could multiply both sides of this equation by volume. So we'd cancel on the right and we'd have volume times pressure equals this constant. So the constant's going to change at different temperatures or if we had different amounts of gas, but as long as those are as long as the temperature and the amount don't change, we'll have some constant. Let's say it's 10. It isn't, but well, maybe it is for some amount of gas at some temperature. But if our constant was 10, I just wanted to kind of illustrate this in a little bit of detail. What this means is any volume and pressure combination is going to equal 10. If my volume was 2, my pressure would equal 5. And this is kind of the basis behind saying that if we have 2 sets of conditions, they're equal to one another. So V1 times P1 equals 10. Well, V2 times P2 would also equal 10. So we can eliminate the constant and just say V1 times P1 equals V2 times P2. Boyle's law. So let's move on to Charles' law. If we look at this graphically, this was by the way, this was studying effects of gases at temperature and volume effects on gases. So we're holding pressure constant and the amount of the gas is constant, and we have this direct relationship. This is a straight line. So we could say right away V equals T, or we could say V is proportional to T. Why don't we start there? V is proportional to T, or we could set V equal to T times some constant, whatever that constant is. So I could divide both sides by T, and I have V over T equals the constant. And just like before, if I have 2 sets of conditions with constant pressure and a constant amount, that they're going to both equal that constant. So this is where we can say that V over T, or V1 over T1, is equal to V2 over T2. They're both equal to that constant, whatever that happens to be. That's Charles' law. Avogadro's law. This was the relationship between amount of gas and volume. So here we're holding the pressure and temperature constant. And if we look at this graphically, we again have this straight line. So we could say V is equal to N, or let's start with the proportional. V is proportional to N. Or I could say it's actually equal to N times some constant. There'd have to be a number there. We used to call it a fudge factor. When you didn't get the right answer, you just made up a constant and threw it into your equation. You guys are going to love P-Chem. So dividing both sides by N, we get V over N equals a constant. And again, I could say, that's one set of conditions. And if I had another set of conditions, as long as the pressure and temperature were the same, they would also equal that constant. So I can just take the constant out and say V over N. You put V over T. It's okay.
I did. Interesting.
It's okay.
I'm still on Charles. No, my pen doesn't want to write. Condition 2.
So V1 over N1 equal to V2 over N2. That's Avogadro's law. Now the next step we're going to do is we're just going to combine these three laws. So if we do this, we end up with V times P over T times N. And this is equal to a constant. And we actually know what this constant is because we have we have a pressure, we have a volume, a temperature, and an amount in moles. And that constant is they call it gas law constant. And it's 0.082057 with units of liters times atmospheres over moles Kelvin. So what this is telling us is that our volume has to be in liters, our pressure has to be in atmospheres, the amount, N, is in moles, and our temperature has to be in Kelvin. And that's really, really important.
Universal gas law constant is R.
Now, the ideal gas law is really what we just saw on the previous slide, and it's just rearranged. If we want to jump back quick, we can see how, we take that PV, our constant is R, so we've got V over P, or V times P over T times N equals, we'll say R, that's the constant. That's the 0.082057. So if I multiply both sides by the N, the amount in moles, and the temperature in Kelvin, I get PV equals nRT. And that's what we have on the next slide. And we call this the ideal gas law. And this is what we're going to use when we have one set of conditions. So if we just have one set of conditions, there's usually one of these we're trying to solve for, we can use this equation. And I've got an example that's really kind of interesting, and that is, what is the volume? So we're going to solve for volume. Now, I could rearrange this equation to get volume by itself. I don't usually do that. I usually just leave it as PV equals nRT. So I have 1 mole, that's my N. I have 1 atmosphere, that's my P. So let me do 1 atmosphere times V, that's what we're going to solve for, the volume, equals 1.00 mole. And R, 0.082057 units liters times atmospheres over mole times Kelvin. And our temperature here at 273.15 Kelvin. We're checking units here, and when we solve for this, what do we get for a volume? 22.4, and the units are liters. Now, you might have heard this before. Like, you might have heard that 1 mole of any gas occupies a volume of 22.4 liters. Well, this is where that's coming from. This is using the ideal gas law, and as long as we're at 1 atmosphere, and these are standard conditions, 1 atmosphere of pressure and a temperature of 273.15 K, that's actually 0 degrees Celsius. But in this situation, we're going to get a volume of 22.4 liters.
Pretty interesting. And it doesn't matter what gas it is. All gases, if it's 1 mole at STP, will occupy 22.4 liters. Doesn't matter if it's a really heavy gas or a light gas, big, small, they're all the same. Very interesting. All right, so thanks for joining us. I hope you enjoyed just a little closer look at some of these gas laws we've been using and how they're related. So I hope you found this useful, and stay tuned. We're going to get into some more detail using the ideal gas law. That's right. Here's your closer look. Bye-bye.